Hello, everybody. Chad, you beat me to it. May the fourth be with you. Okay, so I've started the recording. Can you guys hear me? See the screen?
Yes.
Perfect, thank you. Okay, 5:30. Let me get this little guy here. Okay, we are recording, so we're going to go ahead and get started. So tonight's lecture is going to be about finding deformations in beams and trusses using the energy method. So that's where we're going to start. If I can get this to start, here we go. Okay, so if I remember right, seems like a long time ago, doesn't it? When we started this semester at, when we actually met in person in the campus. And we talked a little bit about energy, and we talked a little bit about work, where the definition of work is a force does work when the force undergoes a displacement dx in the same direction as the force, right? So I seem to remember we kind of drew a picture of a mountain and hiking up to the top of the mountain, and the work that was done was the force, basically your weight, times the vertical distance that you have moved in the direct parallel to the force application, which is gravity. Same idea here. So work is in the units of kip inch, pound inch, or Newton meter. And the equation is dUE. E stands for external work. We're going to have UE, we're going to have UI. I is going to be internal work. And dUE is equal to the integral from 0 to the total displacement of the force times dx. So to kind of demonstrate this topic, we're going to look at work produced by a force F1 from a hanging rod that displaces by delta 1. So I have a rod of some material, and I pull down on it with a force F1, and it's going to displace by delta 1. If I plot that, if this rod stays elastic and we don't get into any funny business, then the displacement is proportional to the force. So if I apply a force of F1, it will displace delta 1. Since the energy UE is equal to the integral of F times dx, then the total energy is equal to the area under the F dx curve, like so. So again, if I apply a force F1 and it displaces out delta 1, then the area under that curve is the total energy that was spent to make that displacement. So then the external energy is equal to 1/2 of that force times the displacement. Since this is a triangle, you get half. Or another way to visualize, the energy is equal to the average force times the total deformation. And the average force is the total force divided by 2. Now picture applying another force, F2, to the rod that's already supporting the F1 force, like so. So it already had F1, it already deflected delta 1. Now we apply an F2 force to it, and it deflects another delta 2. So the graph looks like this. Here's my original force and deformation. Here's the new force. Here's the new deformation, causing the rod to deflect an additional delta 2. The total energy then is equal to the area under the curve. And so the total external energy is half of F1 delta 1 here, all of F1 delta 2 here, and half of F2 delta 2 here. Do I have any questions so far? Okay. So now we're going to talk about the concept of a virtual load. So if I call the F1 force a real force applied to the structure, then the delta 1 is a deflection due to the real force. But I can call F2 a virtual force, usually taken as 1 kip. Just a nice easy number to divide by is 1. So 1 kip is a nice easy number to use for your virtual force. And delta 2 is the deflection due to the virtual force. If I make these definitions, then I can say that, again, here's my chart. So F1 is the real force, delta 1 is the real deformation, F2 is a virtual force, delta 2 is a virtual deformation. So then we can say that my energy, my internal energy, is F1 times delta 2 is this part here. But we can also say that this is equal to, this amount of energy is equal to the amount of energy F2 times delta 1. These are symmetric. So that means that the real force times a virtual displacement is equal to a virtual force times the real displacement. And that's what I just said. The real force times the virtual deflection is equal to the virtual force times the real deflection. Why is this useful? Because if I can know what the internal energy is, then I can find the real displacement by taking the internal energy and dividing by the virtual force. Remember, the virtual force is 1 kip. So the real deflection is equal to the internal energy divided by a virtual force of 1 kip. Any questions? So we can talk about strain energy. Strain energy in a way that any construction material, reinforced concrete, a wood beam, a steel column, any normal construction material, when you put your building loads on it, it's going to cause the material to stress and it's going to cause the material to strain. We've talked about stress and strain all the way back since chapter 2. But if the material is still in the elastic range, when it strains, either in compression or in tension, when it strains, it either compresses or elongates. When you take the load off of it, it will return back to its original shape. The strain will be gone. So in that sense, all construction materials are kind of like springs, where you apply a load to a spring, it stretches out, you let the load go, it returns back to its original shape. So all construction materials store energy like springs. So the strain energy, that's the kind of energy that the material stores internally. The strain energy can be thought of this way. If this is normal stress, so here you have sigma z in the z direction, a normal stress. So from before, the energy is equal to the integral from 0 to the total deformation of the force times dx. So we can call that the force times delta. In other words, if I can solve the integral, then that's force times delta. So the force is the stress times an area, right? All the way back to chapter 2. Stress times an area. So the area happens to be dx, dy, and the stress is sigma z. So the total force is the stress times the surface area. Delta, the deformation in the z direction, is going to be equal to the strain times dz. Again, back to our chapter 3 definition of strain. So the strain is inches per inch times the original length, dz, gives you the deformation. And so I can substitute these back into my equation, and the internal energy is equal to 1/2 times the stress times dx, dy, epsilon z, dz. Or dx, dy, dz is dv, the volume. So now I can say if I take the integral of dui, then the energy, internal energy, is equal to the integral over the volume of 1/2 sigma z epsilon z dv. So now I can use Hooke's law. Sigma is equal to epsilon times Young's modulus E. And I can substitute that back in here so that the energy is the integral of sigma squared over 2E, which all I did is I substituted out the strain here. Strain is equal to E over sigma over E. So I substituted sigma over E back into here. And this is what's known as the internal strain energy, this equation here. Anybody, please stop me if you have any questions. Okay, so we have several different common cases of internal energy. The first one that we'll look at is internal energy due to an axial load. So here I have a bar of some material of length x with a load p. So the strain energy is equal to the integral of the volume. Sigma x squared is the stress on the x here over 2e dv. Sigma x is also equal to p over a. So sigma x squared is p squared over a squared. And if the volume dv is equal to the area times dx, the distance, then I can plug that in here. And now I have, let's see, dv was the area. So one of the area squareds drops out. I got p squared over 2ae dx. And you can integrate from 0 to L. And if a is constant, then the integral goes away. And we can do p squared L over 2ae is the internal energy. Yeah, that's it for that. Okay, so any questions on the internal energy for a bar in tension or compression for that matter? Probably thinking, at least I hope you're thinking, okay, if you say so, well, what's this good for? What am I going to use this for? Well, remember from your statics class that when you analyze a truss is just a collection of axially loaded members that have pinned ends. So there's no moments, there's no shears. All you have is simply supported axially loaded members that are either in compression or tension. So what this can do is for a truss is you can add up the internal energy and solve for a deflection at any given point based on this principle of energy. So kind of tuck this away. This is used mainly for the analysis of trusses. And then we have bending moment. So strain energy due to a bending moment. Remember, a bending moment causes normal stresses. They're just not uniform like a uniaxially loaded member. They are, obviously, you remember from the flexural equation, they are a maximum at the furthest extremes, and they are zero, normal stresses are zero at the neutral axis. So we can look at what the strain energy is induced by a bending moment. Back to my original equation that we had derived, the internal energy is the integral of the volume as sigma z squared over 2e times the dv of the volume, and z is the normal direction from the section. Using the flexural equation that we had gotten, then sigma z is equal to minus my over ix. So I can plug this into here. So I have basically my over x squared is where I plugged it into here, 1 over 2e, and then the volume dv, I can do the volume by finite area of dA. dA is the section area times dz gives you a volume. Now remember, the moment of inertia is equal to the second moment. So it's the integral of the area times y squared dA. And that being the case, then what I can do is, this is I squared right here. And so I can take ix squared out. The integral of y squared is right here times dA. So I can kind of pull those together. So this is the integral of the volume. I can pull the area out of the volume here. I can pull the y squared here and pull the dA here. So everything inside of these parentheses is the moment of inertia ix. So I kind of distilled them out of here, here, and here to distill them into here, which will allow me to simplify this because ix over ix squared leaves you with ix. And so now I've got the integral from 0 to L, this is along the length, times m squared over 2eix dz. Okay, so this is the equation for the energy induced by a moment. Now we have conservation of energy, where the external energy has to equal the internal energy. So now we talk about internal virtual work. And the theory of virtual work is that I can apply a virtual load at the point of deflection. And again, we always choose it to be a 1 kip load. So on a beam or on a truss, wherever it is that I would actually like to know what the deflection is, I apply a 1 kip load in that direction at that point. And then we solve this, and that will tell me what the deflection is at that point. Okay, so again, we go back to this. My real deflection is the energy divided by my virtual load, which is 1 kip. And so if I go to this equation here, this is my energy. So I put my energy here into internal. So my deflection is equal to my energy divided by my 1 kip load, which just divided out. And the virtual load is applied before the real load. So the half factor is eliminated. You notice the 2 is gone from this equation here. In this equation, little m is the moment due to the virtual 1 kip load as a function of x. That's little m here. And capital M is the moment due to the real load as a function of x. When you guys were doing shear and moment diagrams, and we were learning how to find the equations for the moment in terms of x, well, it's coming back to haunt you. Yes, there was a reason to learn that stuff, and that's what this is right here. This is the moment due to the virtual load as a function of x, and we have a moment due to the real load as a function of x. Okay, who's ready for a real world example? So here we have a simply supported beam with a unit load of a linear load of 3 kips per lineal foot. We could find the deflection at midspan. Now, quite honestly, we could find the deflection at midspan by just using the equation we got from last lecture, right? Where we found that the maximum deflection is equal to 5WL to the fourth over 385 EI. Remember that from last lecture? But this is a different way to get to really the same result using an energy method. So in this case, I chose a beam where the moment of inertia is 2,700 inches to the fourth. This is a steel beam, so Young's modulus is 29,000 KSI. And in order to solve this, we need to find the equations for moment for virtual loads. So I create a free body diagram. Now, here's where things get a little more interesting. The problem says find the deflection at midspan using virtual work. I want to know what the deflection is at midspan, so I'm going to put a 1 kip virtual load in the direction that I think it's going to deflect at midspan. That's how this method works. So now I create a free body diagram. This is my virtual loading, and I have to solve for my reactions, and I have to solve for my equations using this virtual loading. If, for example, I wanted to find the deflection at the quarter point, then I would have put the 1 kip load over here at the quarter point. So wherever it is that you're looking for the deflection, you put this 1 kip load in the direction that you think it's going to deflect. Now that I have this, I find my reactions. This should be pretty easy at this point to find this, but 1 kip times half the span is 15 divided by R times 30. R is a half kip up. And by inspection, summing the forces in the Y, RAY is also a half kip up. And you would expect that because this is equally right at midspan. Decide on my cut points. To fully describe this, how many cut points do I need? Well, I have a discontinuity in the middle, right? So I'm going to need 2 cut points here and here. So we create a free body diagram for cut number 1. Cut number 1 is on the left-hand side of the point load. So all I have is my end reaction, positive moment, positive shear. I find my shear is equal to a half kip, but what I really want is my moment. So I sum my moments. I have a half kip times x minus m, so that m is equal to 0.5x kip feet. And this is valid between 0 and 15 feet. Free body diagram for cut number 2. Cut number 2 is on the right-hand side of the 1 kip unit load. And so again, sum the forces in the vertical, I find the shear, and I have a half kip times x minus 1 kip times x minus 15 minus m equals 0. So m is minus 0.5x plus 15. This is valid between 15 and 25 feet, 30 feet. Okay, so here's what you're looking for, even though that's wrong, again. This is the equation from 0 to 15. This is your equation from 15 to 30. This is also, you will see, this looks pretty simple, and it is pretty simple, but this gets kind of messy as we get down the line a little bit. So it is essential that when you get these equations for your moments, you have to simplify these into their simplest form possible, because we're going to be multiplying them together. Any questions so far? Okay. So we found the equations for the moments due to the virtual load. Now we do the whole thing all over again. We have to find the equations for the moment due to real loads. So here's my free body diagram. I take my uniform load times 30 feet is 90 kips so that I can find my reactions. The resultant, of course, is right at the midspan because the loading is balanced and uniform. So finding my reactions, I get 45 kips at B, 45 kips at A, and I have to decide on my cut points. Notice again, this point load, I know I've said this 1,000 times, but this reaction is only valid for finding your reactions. You have to go back to the real loading to find your equations for your moments. I only need one cut point because I have no discontinuities. And so I create my free body diagram, find my shear and moment, sum the forces in the Y for shear, sum the moments, 45 kips times X, minus 3 times X over 2 is the moment arm, minus M, and the equation for the moment is minus 1.5 X squared plus 45X. And this is valid from 0 to 30 feet. Okay, so back to my equation. My deflection, the one I'm looking for, is equal to the integral from 0 to L, little m times big M over EI dx. So the little m is the moment due to the virtual load, which is 0.5x from 0 to 15, but it's minus 0.5x plus 15 from 15 to 30. So how do I deal with this? I have two different equations. Do I just ditch one? Do I take an average? What do I do? Anybody? Any ideas?
Choose separate integrals?
That is exactly right. Thank you. I need two separate integrals. An integral is just the sum under a curve. And I have this curve and I have this curve. They're incongruent. So what I'm going to do is I'm going to take the integral from 0 to L over 2 is one expression, and add that to the integral from L over 2 to L is the other expression. That's how I handle two different functions. Capital M, moment due to the real load as a function of X, I don't need to separate that into two. I have one expression that's valid over the whole span, which is minus 1.5 X squared plus 45X. So here is my expression. Here's my integral. I need to integrate from 0 to 15 with little m times big M over EI plus the integral from 15 to 30 with little m, this little m, times capital M is the same over EI. This is my total expression for delta. And by the way, we had a question last lecture about what would you do if the point load was not at midspan? Remember, we played a trick of solving for the equation of deflection using the double integral method, but only because the moment on the left of the point load was exactly the same as the moment on the right of the point load, and so we used symmetry. And the question was, well, what if the point load was not right in the middle? What if you don't have a symmetric situation? And my answer was, well, then you'd have to do the double integral for the portion that's on the left and again for the portion that's on the right. And it would look more like this. That's how you would accomplish that. What chapter is this all from? Good question. I don't have a clue. I will answer that. Chapter 12. Chapter 12, slope and displacement by integration. Let's see, is the energy in this one? That's moment area, integration, the elastic curve, statically independent. Last homework covered chapter 9. Yes, last homework did cover chapter 9. It's a good question, so let me find it real quick. Chapter 14, energy methods. And what I'm covering right now is in chapter 14.6 and 14.7. That's where it is in the book. Okay. So now what I've done is I have this function times this function times this function. So I multiplied the two together and simplified. And so from 0 to 15 feet, I have to integrate this expression. From 15 to 30 feet, I have to integrate this expression. And so minus 0.75, x to the fourth divided by 4, 22 and a half, x to the third divided by 3, 0 to 15, and so on and so forth. So this is how you evaluate your integrals. At some point, I took the EI, if you notice, and multiplied it, put it over on this side, because E and I are constant for this beam. Now, this part here is just the kind of the more laborious part where you have to evaluate each one of these at 0, or I'm sorry, each one of these at 15 minus each one of these at 0, each one of these at 30 minus each one of these at 15, which is what this is. So these are each one of your terms. And let's see, I got 1, 2, 1, 2, 1, 2, 3 times 2. So 1, 2, 3, 4, 5, 6. 1, 2, 1, 3, 4, 5, 6, 7, 8. 8 terms. And then I condensed it, mathematically down to one expression. The units on this are feet to the third. And then I took feet to the third times 12 inches per foot to the third to get all of this into inches. This is a very key part of this, or a very easy way to mess this up, is to lose your units right here. And then you divide that by E is 29,000 KSI, I is 2,700 inches to the fourth, for a final answer of 0.698 inches. Also, we assumed from our virtual load pointing down that the deflection would be going down. The positive answer means that the deflection went in the direction that we assumed it to be. So positive does not mean up or down. Positive only means it went in the direction that we had assumed it's going to go when we applied our virtual load. And as always, I explained it and then I wrote it. Virtual expand. Okay, so any questions on the beam example?
So for the units for feet cubed, you just went from 12 inches per foot and then you cubed that to get to inches?
Yes,
Okay.
yes, 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 yes. So every one of these feet cubed is 12 inches to the third, which is 1724, something like that. So if you don't do this step right here, you're gonna get this divided by 1724. It's gonna be an exceedingly small number. So yes, you have to be careful, very, very careful with your units. Also, you can do a unit check on this. This is gonna be, the top part here is gonna be inches to the third, I believe. Let's make sure I didn't mess that up. And this is inches to the fourth divided by inches squared. So this is going to be inches squared. Inches cubed over inches squared is inches. So that should be the right units. That's how the units play out. That answer your question?
Yes, thank you.
Okay. Any other questions on this problem? Let's see if this was another way to look at this. I was just thinking about this. So this is kip inches or kip feet. This is kip inches or kip feet. So this is feet squared, and then you're integrating over feet. So kip feet to the third. So this whole top part becomes, yeah, you know what? I forgot. I lost that. There's kips in here. I got to fix that too. I'll make a note of that. I forgot my kips. This is slide 136. Kips in delta. Okay, sorry to slow you guys down. What I'm mumbling to myself is that this unit right here, 31,600, this guy right here should have kip feet to the third, so that when you divide by kips over inches squared, the kips will wash out and not be part of the final answer. And those kips came from these kip inch moments up here. Okay. Next example is we're going to find, I think I went all the way to the end. That was a spoiler alert. There we are. Okay, I want to find the deflection of this truss based on the virtual energy method. So on this truss here, the real truss has these dimensions, 40 feet, 40 feet, 40 feet, 15 feet high. It has these members labeled with an A1, have an area equal to A1. These guys in here are smaller. They have an area equal to A2. And the loads are not symmetrical, as you can see. I got 20 kips, 40 kips, and 40 kips. I would like to find the deflection right here at C going down. So that's the problem statement. So the A1 sections are 4 inches squared. The A2 sections are half of that, or 2 inches squared. This is made out of steel, so E is 29,000 KSI. And I solved the truss for a virtual load of 1 kip applied at the point of deflection here. And so here's again like a free body diagram of the problem. I have an unknown reaction at A and E and a 1 kip virtual load at C. So I have to solve all the truss forces with the virtual load. So first I'm going to find my reactions. If I sum the moments about A, I find the reaction at B is half a kip. And again, it's symmetrical, so we would expect that. Sum the forces in the vertical, and I have a reaction at A of half a kip. And then we use the method of joints to solve this truss. You guys remember method of joints from statics? Okay, I got 31 participants so far. We're 50-50. Kind of. It's been a while. Yes, barely. Okay. But you've seen it before. Not good at it, somewhat. But you have been taught this before. Semi. Yes. Okay. Method of joints. So the sloped members, first of all, we'll talk about the sloped members. Because of that 40/15, they are all angled at this 3, 4, 5 triangle relationship. So you start with one joint. Usually you start at a joint where you know something about it, and then you solve for the unknowns. So the method of joints is always you start at a joint, usually one that has a reaction, so you know something about it, and you draw in all of your unknown truss members in tension. So you always draw them pulling away from the joint in tension, because remember, tension is positive, and if you get a negative, then you just know that it's the opposite, and you have compression, not tension. So here is member AB going away at a 3, 4, 5 triangle angle, and AC is horizontal, and my reaction was 0.5 kip. Trusses are pinned at all ends, so there are no moments. So I can't sum my moments. That doesn't get me anything because they're all 0. So I only have 2 equations I can work with. Sum the forces in the X, sum the forces in the Y. That's another reason why you want to look for a joint where you don't have more than 2 unknowns, because you can't solve it. You only have 2 equations. So joint A is perfect. I have 2 unknowns, and I can solve this. The one I want to solve first, if you think about this, AB has a component in the Y direction, but it also has a component in the X direction. AC also has a component in the X direction, but not in the Y. So I'm going to start by summing forces in the Y direction because I only have one unknown in the Y direction. And that way I don't need to create a system of simultaneous equations with 2 equations and 2 unknowns. I don't need to do that if I can sum them in the direction and isolate the one that is the only one that has a component in the Y direction. Did what I just say make sense? Or is that clear to everybody? Okay. So I could either start with X and have 2 unknowns in one equation and I can't get anywhere, or I could start with Y and solve directly. Sum the forces in the Y. I have a half a kip going up is positive, and I have 3/5 of AB going up. So half a kip plus 3/5 of AB equals 0. AB then equals minus 0.833 kips. Negative means that it's in compression. Okay? Everybody all right with the quickie way of getting your components? Anything at an angle is going to be 3/5 or 4/5, depending on which component you're looking for. Now that I have the Y, I can sum forces in the X. The component of AB in the X is 4/5. So I have 4/5 of what I just solved is minus 0.833, plus AC is positive in the right, So AC is equal to 0.667 kips tension, positive to the right. That's joint A. Now we move to joint B. Now joint B, I solved AB and I know it's in compression. So if it's in compression, it's pushing into joint B. BD and BC are unknown to me at this time, so I draw them tension pulling away from B. So here again, I have only one unknown in the Y direction. I have two unknowns in the X direction. So I sum my forces in the Y direction first, and I get 3/5 of 0.833 is the compression element, minus, because it's going down, minus 3/5 of BC is equal to 0. BD has no component in the Y direction. So I can solve directly. BC is 0.833 kips in tension. Sum my forces in the X. I have, again, this vector here, 4/5 is a horizontal component, plus 4/5 of BC, that's positive because it's going in the same direction to the right, plus BD is going to the right, is equal to 0. Add these two together, BD is equal to minus 1.33 kips in compression. Any questions so far?
The method of joints, when you're drawing all the members, is it best to draw them all in tension, or can you draw some in tension and others in compression?
Always draw the ones that you don't know what they are yet in tension.
But
The
let's say
ones-
like you.
Go ahead.
Oh, my bad. Go ahead.
Okay. Whenever you go to a joint, anything that's been solved, draw it the way you know it's going to be. Anything that has not been solved, draw in tension.
Oh, okay. Gotcha. Thank you.
Does that make sense?
Yes.
Okay. So moving to joint C. And if you remember the shape of the truss, I'm just kind of moving along to the right here. So at joint C, I have already solved for AC, and I've already solved for BC. Both of these solved to be in tension, so I'm drawing them as they are in tension. CD and CE, I don't know yet, so I draw them in tension. And don't forget, this is the joint where our 1 kip virtual load is being applied. So now, if I sum all my forces from the Y direction, I have 3/5 of this 0.833 going up. I have 3/5 of CD going up, and I have minus 1 kip. And so solving for CD, CD is 0.833 kips, and it is in tension. In the X direction, I have negative 0.667 because it's pulling to the left. I have minus 4/5 of 0.833 because it too is pulling to the left. I have plus 4/5 of 0.833 because it's pulling to the right, plus CE. CE is positive 0.667 kips, so CE is in tension. Moving to joint D, I already solved for this was CD. BD, I thought I already solved that one as well. And then DE is unknown. And so then I solve the forces in the Y. BD has no Y, so 0.833 kips. And this is minus going down 3/5, minus 3/5 DE. DE is 0.833 kips in compression. And I had already solved for BD, so I didn't do the sum of the X's. So here's the final layout. This is what we just solved. I just put all these results right back onto this diagram, labeling everything with a T or a C to indicate compression or tension. Okay, so this is this truss solved for the virtual load. Any questions on this? Okay. So now we have to do it all over again. Isn't this fun? Now we solve the truss again with our real loads. So I need to find my reactions. I know this isn't a beam, but in terms of moment arms in the horizontal direction, it's easier to visualize the truss with the 20, 40, 40 kips as a beam. And we can find our reactions by just summing the moments and divide by 80 is the total width. I get 55 kips on RBY. And summing the forces in the Y direction, I get 45 kips on the RAY. So at A, I have 45, at B, I have 55. As you can see, it's not symmetric. Okay, we're going to do it again. All slope members are still at an angle of 3, 4, 5. I start at joint A, but now I got 45 kips. And basically doing exactly what we just did, only with the new reactions, I find that strut AB is 75 kips in compression, and strut AC is 60 kips in tension. At joint B, now here's probably the easiest way to mess this up, is to forget to put on the real loads. So there's a real 20 kip load at joint B. So summing the forces in the Y, I have 3/5 of this 75 up. I have 3/5 of BC unknown down, and I have 20 kips going straight down. So BC solves to be 41.667 kips in tension. Now I sum them in the X direction. I have 4/5 of the 75 positive to the right. I have 4/5 of 41.667 positive to the right. And I have BD unknown. So BD sums or equates to be minus 93.334 kips. And it's negative, so BD is in compression. I move to joint C. I label the two that I've already solved for. This was AC and BC. So I put them on there, and they're both in tension, so I draw them in tension. I draw CD and CE, my unknowns, in tension. And don't forget your 40 kip load applied at C. Sum the forces in the Y. I have 3/5 of the 41.667. It's up, so it's positive. And for CD, I have 3/5 of CD up, so it's positive. And my 40 kip load is down. So CD sums to be 25 kips in tension. Summing my forces in the X, I have my positive 60 kips pulling to the left, so that's negative. I have 4/5 of 41.667 to the left is negative. 4/5 of my 25 that I just found to the right is positive, and CE is assumed to be to the right and positive. So CE is 73.334 kips tension to the right. And joint D, and again, I have this BD in here even though we just solved for it. But we know that CD is 25 kips here. So 25 kips tension is pulling down, 40 kips pushing down, and you have DE assumed in tension. Solve the forces in the Y. I have 3/5 of 25. It's down, so negative. 3/5 of DE. It's down, so I assume that's negative, and 40 kips is down. DE sums to minus 91.667 kips, negative, so DE is in compression. And there's my findings. So I took each one of them and superimposed it back onto truss. Okay, So far, so good. Everybody all right with the method of joints? Okay. So now we get to strain energy. If A is constant, then the internal energy is P squared L over 2AE. Conservation of energy, internal equals external. So my internal virtual work, I apply a 1 kip load at the point of deflection, and I solve, again, the same thing, delta 1 is equal to the internal energy divided by my unit load. So this is where it gets a little different. This is how you apply it for virtual work. You do have to still integrate from 0 to L. Little n is the little n is the force due to the virtual load. Big N is the force due to the real load divided by EA, Young's modulus and the area, and then you're integrating over dx. Virtual load is applied before the real load, so the half factor is eliminated again, same as before. Little n's axial force due to the virtual 1 kip. Big N is axial load due to the real load. And then what we're going to do is set up a table, as you can see. So the area is constant. So this is going to simplify. We don't need to integrate over the length dx because everything in here is constant over the length dx. So we're going to set up a table. Here's all of my truss members. Here's the length of those truss members in feet. Here's the area in inches squared. Here are the loads that we just found due to the virtual load. Here are the loads we just found due to the real load. And then what I've done here is I've multiplied little n times big N times L and divided by A to get this sum here. And at the bottom here, I have the sum of each one of my members. Because again, the work, the strain energy of the whole truss is a collection of each truss member's own strain energy. So it's kind of like you have an assembly of springs. And you put a load on this thing and all your springs are storing up some energy. Whether it's in compression or in tension, it's still energy. So now we're adding all these together to get a total for the whole system of little n, big N, L over A is 3,695.36 kips squared feet over inches squared. And so the final step is we're going to take that sum that we just found. We're going to multiply it times 12 inches per foot to get rid of that foot right there. And we're going to divide by Young's modulus here, KSI, to get a total final deflection of 1.529 inches. And again, the deflection is positive, so therefore it is in the same direction as the 1 kip virtual load that we had applied, which if you remember, we applied it going down. So the truss does in fact deflect downwards. Okay, let me back up a couple slides. So any questions about this? So basically what we did is this is the equation for the strain energy of one member that is L long. And so we found the energy of one member, that's this guy here, but we add the energy from all the members to get a total energy for the system. Okay, now, is this going to be on the final? So what did we do in the last 2 weeks? We did, strain transformation. Then we did, gosh, I'm already blanking out. What was the lecture before last? Yeah, we'll use. Okay, so we did. Okay, yeah, strain transformation, deflection of beams, displacement by integration, and then we have one more lecture after this. Okay, so we have a few minutes left. Actually, I have 15 minutes left. So yeah, I will address that. We'll talk about that. The stuff that we did homework on was up through basically chapter 9, if I remember right. So we did homework on horizontal shear. We did homework on stress transformation and Mohr circle. So the stuff that we did homework on most certainly is wide open for the final to do a calculation type problem. The stuff that we have not done homework on, I'm not sure about strain transformation. I'm thinking strain transformation, displacement by integration, deflection of beams by integration, deflection of beams by energy, and then this last one we're going to do on column buckling. Those topics that you have not done any homework on, they are still open to the final, but they will not be a calculation type problem. They would be more of, and I haven't written the final yet, so don't quote me on this, but if those topics are on the final, they will be more in a kind of a fill the blank, make sure you were listening, make sure you read the book type of problem, not a part A through D calculation type problem. Okay? So say that, yeah, let me say that one more time. So everything that we've done up to stress transformation and Mohr circle is wide open on the final. All of that should be studied for and practice with doing example problems. Everything that we did since Mohr circle, which includes strain transformation, beam deflection by integration, beam deflection by energy, and column buckling, could be on the final as a fill in the blank type problem. Okay, does that answer your guys' questions? Okay, and this stuff that I just presented here on truss, finding deflections in trusses using the energy method, absolutely go ahead and use Excel. That's the way, that's why they invented Excel, was to do beam or truss deflections due to energy. I'll bet you anything. You ask Bill himself, why did he invent Excel? It was for that reason. Okay. Any other questions on this, or at this point, basically wide open if you have any questions about anything else we've done, or the last lecture, which is on Wednesday, or the final, which is a week from Wednesday.
So, so the things for that you were lecturing about today and next on the next lecture are going to be more conceptual / fill in the blank kind of stuff on the final?
They could be on the final.
Okay, okay. So,
right, so
should we redo the past two homework like over and over again, like as practice to study for the final?
Okay. First of all, very quickly, Shin asked, can we use Excel during the final if there's a question like that? I will not ask you a question that you have to use Excel, because I believe the way the Respondus works, you can't open an app, so you can't use Excel during the final. But I will not give you something that you have to use Excel for. Okay, and then back to your question. The final is going to be geared more towards everything that we learned since the last midterm. The last midterm covered up to chapter 6.4, which was the flexural equation. So finding moments in terms of X, finding the equations of moments, drawing the shear moment diagram using graphic, and the flexural equation was all on the last midterm. So everything we've done since then, which includes combined loading, biaxial loading, combined loading, stress transformations, strain transformations, and everything I just rattled off in the last week or so is kind of what it's more geared towards. But remember, this final is comprehensive. And this final is really kind of like the last chance for you guys to prove to me that you've gotten the essentials out of this class before you move on to wherever your career moves you on to. So hopefully that makes sense. It's not all going to be what we've done since the last midterm, but it's going to kind of concentrate on what we've done since the last midterm. So in a nutshell, and Juan, I'll get to your question in just a second, but in a nutshell, yes, you should practice those fundamental things that we've done since the last midterm. And if there's anything that was like not clear or difficult for you to do, practice those things. Horizontal shear was not on the last midterm. We did that since then. So those are the topics that I would spend most of my time on. But at the same time, look at your first midterm, look at your second midterm. And if there was any topic on the first or second midterm that you just flat out like, wow, I did not know what I was doing. I don't even understand what the answer was. I just didn't get that. Make sure you go back to the first and second midterms and understand those topics, because those topics build up to what we've been focusing on for the last couple of weeks. So does that make sense?
Yes, thank you, Professor.
Okay, very good. Juan, are we going to review on Wednesday? If we are you going to upload it on YouTube? We could review a little bit more, because I'm pretty sure the column buckling is not going to take us the whole hour and 15. So we can review a little bit more, and I am uploading each one of these the next day, but I'm uploading each one of these to YouTube. You can find them all there. And I might be writing the final this week, so I might have a little more direction, but basically what I just said is really what you need to study for. Final like questions? No, I'm not going to do final like questions. Really, it's, how I test at this point now. You know that the first midterm was a lot like the essentials of the homework, and the second midterm was a lot of the essentials from the homework. You know what the final is going to be like. All right. Is that okay, Caesar? I don't have time to prepare more stuff. Basically, just keeping ahead of you guys. Okay. Did any of what I just said not make sense, or any other clarifications you think you need? Okay. As I said, I will save this lecture and we'll put it on YouTube. We'll have one more lecture. Don't forget, if you have any questions, I have office hour from 4:30 to 5:30 on Wednesday. And I don't really have office hours the following week, the week of finals, but if somebody wants to talk to me, just email me and I'll set something up if you want to talk to me during finals week. But I will be on here 4:30 to 5:30 on Wednesday for any last minute questions that you might have. I urge you, please, please go over your midterms, see what was the problem. If you had a problem, see what the problem was, and feel free to ask me about it. The second midterm, if you haven't done so already, if you don't know what the problem was, get with me in an office hour and I'll open up your midterm so that you can see where you lost the points and where you were struggling. We can do that, but that's only a one-on-one. So let me know if you'd like to see how you or what happened on your midterm too, and we can take a look at that. And again, if the timing doesn't work, email me and we'll try to work out some other time when we can do office hour so that we can answer any questions you might have before the final. If there's no other questions, then I'm going to end this now, and we will see you on Wednesday.